Okay. Hi, everyone. Welcome to the last session of the MoCaO lectures for this week on derivative-free optimization. Very glad to have with us Sara Shashaani from North Carolina State University. So Sara is an associate professor and Bowman faculty scholar in industrial and systems engineering at North Carolina State. She got a PhD from Purdue University, a postdoc at University of Michigan. She was a 2024 Goodnight Innovator, a 2025 MGB SIME Early Career Fellow. She's had a lot of success in her career so far. Within the kind of the DFO context of what we've been talking about this week, Sara's done a lot of work on stochastic optimization, particularly in the context of simulation-based optimization. So dealing with some very complicated sort of Monte Carlo type simulation problems coming from the motivation. And she's made some nice contributions to theory, algorithms, and software. I very, very briefly, Sara mentioned Astro at the end of my talks to flag it as a useful piece of software. And that's part of this broader SimOpt package that's kind of a generic simulation optimization framework for simulation test problem solvers and so on. So we're very glad to have Sara here to talk about stochastic DFO. So over to you, Sara.
Thank you very much, Lyndon, and good morning to all of you in Australia. It's a pleasure to be here and present AstroDF a little bit more, as you have heard in the previous lectures. I'm going to start with first acknowledging my collaborators. I realized just after I shared my screen that I have these two pictures very far apart, but actually Yunsu, who was my former PhD student and currently a postdoctoral scholar at Cornell University, and Raghu Pasupati, who was my PhD advisor when I was at Purdue, are really the central collaborators for the work that I will present today. And I'd like to also acknowledge some of the financial support that has supported our research, as you can see in this slide. All right, so as Lyndon alluded to, the focus for my research during PhD and after has been simulation optimization, where your function is in the form of a black box, but it's a noisy black box. So if I wanted to minimize my function, I would actually have to run that black box function multiple times at a fixed point x to get an estimate of what would be the expected value of function capital F of x and c. So the formal problem would be minimizing the expected value of capital F of x and c. Generally speaking, we don't usually have a way of going about proving convexity or anything like that. So it's very common for simulation optimization problems for us not to assume convexity. So we go with possibly non-convex function f. So the expected value function is possibly non-convex. We have the unbiased property, which means that indeed the expected value equals the function, and we will have this variance of the random function values capital F for a fixed x. So I'm going to call this variance function sigma square f of x. This is what's called a zeroth order oracle because it only gives me the function value. And as you might guess, if I wanted to estimate this little f of x, I would run this oracle say n times with IID streams of random numbers. So those J's would be independent and identically distributed. And then I'll look at this sample average value that I'm going to denote with f bar of x and n. So that would be the estimated quantity. It does happen sometimes even in simulation optimization settings where you will have a black box problem, but it does give you both the zeroth order and the first order information. So you will, for a fixed x, you actually get both outcomes of your black box simulation. What this means often is that in addition to your a function being unbiased, so the expected value of capital F of x and c being equal to little f of x. You also have unbiased gradients. Expected value of g of x and c in this case will equal the grad f at x. And, we can also kind of have this notion of variability or variance. So a common thing to do here is to look at the covariance matrix of your random gradient values at the fixed points x, and you can actually define this sigma squared g, and then later we'll see what kinds of assumption we can make about these. So in this case, I can again estimate both function and the gradient. So I call that G bar just to be consistent with my notation, which means that again, I'm doing a sample average quantity or sample average approximation for the function and for the gradient, again with IID samples. Okay, so just to get a sense of how can we get this first order information, this is a simple operations research kind of a problem where you have a news vendor problem. So in this problem, suppose that you want to maximize your profit, say by the end of the day. Your decision is how much to buy the commodity of interest, say X amount at the beginning of the day. And, you have certain purchase cost for that commodity. You have a selling cost of P. And then whatever you cannot sell at the end of the day would be salvaged with the price of W. But what you don't know during that day or at the beginning of the day is the demand. So if I wanted to write this random function f of x and c, this would be basically the formula for the profit. And I can indeed differentiate this function, although it has point of non-differentiability, but I can say for, for x's that are less than c, a realized demand value, I'm going to have it's basically a piecewise linear function, right? So I'll have a slope of these piecewise linear functions to be defined as you see on this screen. So indeed I can think that every time that I'm running my oracle, I'm not only getting for a realized demand the profit as a function of the x, but also the gradient, right? Because once I have the realized demand, I can know what the gradient would be at that x. And then I can simulate this for multiple demands that are IID generated, and then I'll do sample averaging as I was showing earlier. This was also an example that Lyndon introduced in the applications of derivative reoptimization. I just wanted to quickly point to that as well. So because this example also captures the difficulty we have with this simulation optimization problems, because if I a priori fix a certain number of random instances, this case would be the bus arrival problem. You might recall we want to basically find or schedule a second bus in order to minimize the average waiting time. And so in this case, our random object is actually basically a sequence of the passenger arrival times. And so ahead of time, I would need to decide, okay, how many of these streams of arrivals do I want to generate? And then I would be calculating the average waiting time of the passengers for different values of that second bus schedule time. And these functions you can see for a fixed realization of these, or a fixed number of realizations of this stochastic system would basically look like a piecewise linear function like you're seeing here as well. And so in order to know, for example, how do I get closer to the true solution? If I fix my sample size, I will indeed never have convergence properties. So in order to actually converge to the true solution or the solution to the original problem, then I would need to really investigate how do I choose the number of random realizations that I want to generate for my problem. Also, a quick note here that although we talk about simulation optimization, just like I was showing you in the earlier slides where we were doing sample average approximation, even in the machine learning setting, you could transform the machine learning type problems where you want to, for example, minimize a loss, for your observe between your observations and your machine learning model. You could consider this as a sample average approximation, which is actually approximating an expected value function. And therefore, if, for instance, we had a very large number of data points, formulating this as simulation optimization will allow us to do the same kinds of sampling analysis that would lead to, certain algorithms that could hopefully improve sample complexity of training a machine learning model. So it doesn't necessarily have to be, the framework doesn't necessarily have to be applied only when you have a black box random stochastic simulation. And before I go further, I just want to say that for the purpose of this talk, the standing assumptions that we have for the rest of the presentation is that our original or our underlying function or expected value function is smooth, so its gradients exist and we don't just have access to them even in the zeroth order case, even in even noisy gradients aren't available. So that's kind of more similar to the derivative-free optimization formulation that you have seen in the deterministic setting. And then another common assumption is about the noise or the variability of these function and gradient observations, as I had defined in the earlier slide. So oftentimes a finite variance assumption is made for proving convergence and analyzing algorithms in this class of problems. Okay, so you might recall from the earlier lectures this week that one of the workhorses of optimization are first-order methods. So you've seen the steepest descent algorithms or gradient-based methods. It turns out when we move to the stochastic setting, you can apply the same first-order methods, but you have additional requirements in order to be able to handle the noise. So one of the very early algorithms in this setting was proposed by Robbins and Monroe in 1951. Commonly known as stochastic approximation, and you might even say, well, this is very similar to stochastic gradient algorithms. So here I'm just going along the negative of the realized gradient, and I have this step size AK, and in order for this algorithm to work, I would need to choose this AK to go to 0 at a certain rate. So it has to go to 0, for example, at a rate that's, a common choice for this would be, for example, order 1 over k to the power. Oh, sorry, I'm missing an alpha here for the power of k plus 1. So it would be basically a step size that's decreasing but slowly. And the goal of that is to essentially, as I have pointed on this slide, to average out the noise while moving towards the target. So this is if you do have the first order oracle, right? So I do have access to this G value at a given xk, and I can just, realize the ck plus 1 and then plug that into this formula. If I don't have that, if I'm in the zeroth order oracles, then finite differencing would be, of course, one of the intuitive things here. So you've seen finite differencing in this case for us because everything is random. I could estimate my gradient at xk with this nabla hat f of xk using finite differencing, say with perturbation size of ck along the coordinates. This algorithm by Kiefer-Wolfowitz in 1952 suggested that you can essentially use the same analysis framework that we had for Robbins and Monroe, but you would need to have additional requirements for the perturbation size CK as well. Because you can see, as you know, obviously, as the perturbation size goes to 0, we're going to have better and better approximations of the gradient. However, in the estimation process, you have a bias and a variance. So the bias of your finite variance approximation can go down, but your variance can blow up. So the way that you have to balance these two is by ensuring that AK and CK are chosen to satisfy these two requirements that you see in the slide. And a common choice for this would be, sorry, I showed you the next block of algorithms as well, but the common choice here would be just to have a AKB, order 1 over K, and having a CK that's 1 over the 4th root of K. So as you see in the top part of the slide, the Kiefer-Wolfowitz algorithm requires that you evaluate if you are in a d-dimensional space. So I forgot to say this in the earlier slide, but I have switched from n being the dimension to d being the dimension because I'm going to use n as the sample size for the rest of my talk. So hopefully that won't cause confusion, because I know that n was used by Linden and probably Zaikun also for the dimension. So here you can see that I would have 2D different function evaluations per iteration. And that would be problematic. So one algorithm that's called simultaneous perturbation stochastic approximation, which should remind you a little bit of the randomized methods for finite differencing, was proposed by Spall in 1992. It's short for SPSA. And it essentially says that we're going to use a random perturbation vector, UK, where each element of it will have a value 1 or -1 with probability 0.5. And we're going to use just 2 function evaluations in this case instead of 2D. So we're saving some computation this way. And all of these algorithms, I didn't put the requirement is similar to Kiefer-Wolfowitz in terms of choosing the perturbation size and the step size. However, there are really no convergence rate analysis results that would help us see how they would do in practice. We do have a version of this code in our simulation optimization library that I'm going to show you in a few slides. So in the previous stochastic approximation class of algorithms that you saw, we always basically realize or evaluate our gradient or function values depending on if we are in 0th order or 1st order oracle. And that would, so the realized value would change. You note that I have carefully chosen this Xi to be a function of K, so it could change. You could have independent random number streams that you use to run your simulation. But another large class of algorithms are the sample average approximation algorithms. So these really, I would say these are not really per se algorithms, but ways by which we can directly use deterministic algorithms and deterministic analysis of those algorithms for stochastic settings. So the idea is that we will actually, instead of solving the original problem, we will solve this sample average approximation problem with a fixed n. And not only our n is fixed, but also our random number streams or random numbers C's are going to stay fixed, which is a concept that we call the common random numbers in the simulation literature. So you really are dealing now with a deterministic problem because you have fixed those X's. So you can think of this f of x and c, where you have fixed x's and now you have a function of x, but for a fixed C. You have, say, n of those functions. So you have moved from a stochastic space into a deterministic space. Now, how well would we do in this setting, or how would we choose this n in order to find a solution that's good enough or close enough to the solution to the original problem? Shapiro has a result on this where if I was interested in a set of delta optimal solutions to this Pn, which is my sample average approximation problem, and I wanted that to be contained in the set of epsilon optimal solutions to the original problem with a high probability of, say, 1 minus alpha, where I would pick a smaller threshold, stationarity threshold for my sample average approximation problem, we would need our sample size to follow this formula. And I don't really want to go through every piece of this formula. What I want to say is this result is for when your feasible space is compact. And so you can have a diameter, if you will, is capital D value for your compact feasible space. And you do also have a Lipschitz function. If you think of a simple example with like an epsilon of 0.1, delta that's 0.05, and then choosing moderate values for the rest of these parameters, and you plug them into this formula, you will see that your n will be a very large number, 167,000. So what it says is that you're evaluating 167,000 realizations of your random function for all x's that you need to estimate your function at or evaluate your function at. So you can see that for a black box problem that may or may not be expensive to run, this is not very useful. This is going to be very computationally intensive. And so we have, in the recent decades, we have moved away from fixing our sample size ahead of time and then seeing how we can actually adapt it by means of things we learned from the algorithm itself. So with this, I want to move to the model-based methods. You learned a lot about model-based methods this week. And in the unconstrained optimization of zeroth and first order stochastic oracles under bounded variance, what kinds of results do we have? First of all, some notations here that I will be using throughout the slides. If I had an algorithm that generated a random sequence of iterates, xk, then I would be interested in complexity results of these algorithms in terms of how many iterations do I need to reach epsilon stationarity. This is should be a well-known quantity for you. So the first iteration at which the gradient norm falls below epsilon. But since I am now in this black box noisy setting, maybe that doesn't tell me necessarily how long should I run my algorithm, because it could happen that I will have various number of simulation runs per iteration. So the iteration complexity, or T epsilon, may not necessarily tell me about how efficient my algorithm is in practice. So we will think about this number of total oracle runs in order to reach epsilon complexity. And you can think of this as summing up all of the sample sizes. So I'm going to use a capital NK I here, because this sample size may or may not be random. And in stochastic simulation, we have a habit of using capital letters for random variables. And so I switched from little n to capital NK of I to allow that to potentially be a random variable. And in addition, since we are going to be thinking about both first and zeroth order stochastic oracles, it may be the case where we might need to evaluate many points just for one iteration. So let's call the tau k the total number of points we're evaluating at iteration k. Now with this, the table below is a non-exhaustive list of some of the, I would say, recent, relatively speaking, algorithms for model-based algorithms, starting with the Deng and Ferris algorithm from 2009. So you can see, except for the algorithm by Larson and Bloves, most of these actually ended up using variable sample sizes. And you can see some of them have results on expected number of iterations to reach epsilon stationarity. And we have some more recent work for an algorithm called STORM that also has an expected sample complexity. So this W epsilon, by the way, we call it sample complexity because that's just total samples, total number of samples, if you will, or oracle runs to get to epsilon stationarity. The bottom two are results we have for AstroDF, which stands for Adaptive Sampling Trust Region Optimization. And we have two versions of that for the zeroth order oracles. We call that AstroDF or derivative free, and Astro for the first order. And you see that we match the expected complexity in terms of iteration complexity with the literature. And in terms of the sample complexity, we have epsilon to the -6, which is similar to what STORM algorithm achieves. We are also able to use some variance reduction features to further reduce the rate of sampling and therefore the total sample complexity of AstroDF and Astro. One thing I was going to talk about a little bit is that we do have almost show results on both of these algorithms, which is going to be important in certain cases in practice. So I wanted to spend just a few minutes to talk about that. So what kind of probabilistic guarantees can we get from simulation optimization algorithms? If we don't really have knowledge of how large is the variance of our function, what is the noise level, that's another terminology used in this setting. Or for example, if I had first order oracles, how large would be the variability of my gradient, random gradient values, and other important parameters. Then what kind of probabilistic guarantees can I get from my algorithm, right? So one most commonly used guarantee is the inexpectation guarantee that says expected value of the norm of your gradient converges to 0. What this means is that if you ran your algorithm multiple times and you actually looked at each iteration and you average what the gradient of the X that algorithm generated in multiple runs was, if you were able to estimate it, then on average you should expect that these quantities will converge to 0. But then again, in practice, one of the challenges here might be, okay, how many times should we really run this algorithm in order to trust that the average value is going to be behaving as we expect here? Another one is if we have results that are in probability. So, for example, I might say that I'm interested in an algorithm that has a guarantee that the probability of the gradient norm is less than epsilon for a fixed epsilon, for example, goes to 1 as k goes to infinity. And so the way that we can interpret this is that if I run my algorithm many times, a fraction, there's a probability or a fraction of these runs are going to be getting close to epsilon, but as k increases, this fraction grows to 1. So if I basically look at a fixed k, then that less than one fraction would be something, for example, if we ran the algorithm, we don't know if that run is actually among those that are going to be behaving converging in the way that we expect. And the last one is the almost surely result. This would be a stronger result, although it has an asymptotic interpretation. But what this means is that if I can get an algorithm that has an almost sure convergence guarantee, that means every run of the algorithm that has a non-zero probability will reach, for example, an epsilon close to reach an epsilon close solution, but maybe at various times. But what I know is that if I ran my algorithm just once in practice, I know that that one run, if I ran it long enough, it is going to converge. So it does, basically you feel that you can basically use this one run and just, for example, in practice, run this for a period of time to see how close you're going to get to your stationarity. Okay, this is a figure of, oh, I thought I had SPSA on this plot, but I actually didn't. So SPSA, in some of the other plots that we have, you might find them on the CMAP library or in some of the other papers that I have cited here, actually wasn't very competitive with the ones that you see in this plot. This is just to test some of the first order model-based and other derivative-free algorithms like Nelder-Mead, if you may have heard of that, on a suite of problems that are non-convex from our simulation optimization library. This plot, essentially is showing us as we use increasing fraction of our budget, and here budget for us is the total number of simulation runs. So if I said that for every problem, I'm going to give it a certain budget of total runs. As I'm getting closer to that, total run, what percentage of these problems am I able to solve to, say, 10% optimality? In this case, it's what we call 0.1 solve time at the top of the plot. And here you see AstroDF, and you can see Storm that was in the earlier slide. We have two first order methods here, Adam and Aloe. We have other plots also with Kiefer-Wolfowitz and SPSA, as I mentioned. I did not include them in the slides, but we were happy with the performance of this algorithm. And so we're going to talk a little bit more about what is the advantage of using adaptive sample sizes here. And just a quick plug here that please feel free to use this library. We have real simulation problems here. So as opposed to using this deterministic problems and just synthetically adding noise to them, we have problems such as those that you have seen so far in our library, where the noise behavior is really going to be a lot more complicated than, for example, a synthetic additive or multiplicative noise with different heteroscedastic tail behavior. So we find this to be a good test bed for those who are interested in developing algorithms for this class of problems. Okay, so now let me switch to analysis a little bit. Recall that in the deterministic setting, I'm going to follow what you saw in the, I believe it was the first or the second lecture, where we just used linear models just to simplify the analysis a little bit. So let's go back to that, quickly refresh our memories. So suppose that you are in a model-based setting, you're building your model as such, as a linear approximation, and assuming that this gradient approximation GK is obtained using finite differencing, with a perturbation size of C, you've seen that you can write the model error, if you will, at an arbitrary point y that's within delta k neighborhood of your center point xk. You can decompose this with the triangle inequality of these two terms. So the first term is essentially we write it to leverage the Lipschitz continuity of the gradient. So we can get this L over 2 y minus x bar squared. The second term is going to be the finite differencing error, and you have seen this before as well. So we have these two terms, and in order to basically make both of them order delta k squared, I would need to choose my perturbation size to be delta k, so the size of the truss region. And this is where we saw that delta k in the derivative-free deterministic setting plays multiple roles of making sure the step size is basically controlled in an adaptive way rather than choosing it in a, or prescribing it, for example. And model accuracy is also controlled with delta k. And finally, termination. And this last one, as you might recall, is why we need criticality tests in derivative-free algorithms, because instead of directly using any gradient or gradient approximation, we would want to use this delta k as when to stop the algorithm. So we would ultimately want delta to really track the true gradient. Using finite differencing, we do have the gradient approximation to be ordered delta, and therefore we have to enforce that our gradient, the model gradient norm, is also ordered delta in order to achieve this. So that's what's called the criticality step. And if now I move to the stochastic setting, I'm going to again switch to capital letter for my model, capital M. Here I don't have the function, and I replace it with the estimate. I'm going to use sample size nk. And for the gradient, I will use the same finite differencing, but instead of using the exact function values, I'll use function estimates, right? So you can decompose this into, if you had the true function values, you would have a gk, and then the error would be basically e bar. So here, e bar is the true function minus the function estimate, if you remember from the earlier slide. So at each of these interpolation points or perturbed points, we're going to look at the estimation error, and this is what we're going to get for the gradient. So things look very similar to what we saw in the previous slide, but here we would need to handle the error in the function values, right? So you can see that we have an additional term in red, which is the difference between the two estimated errors. One at the center point xk and the other at the point that we're interested in, say y. And then you have this third, the term that we had in the previous slide, we had a little gk. Now we have a capital gk here, since that's what our model uses. And so here, I also have another. If I look at what the error in my gradient is going to be, it's going to have, that y minus xk norm times LC, but it's also going to have an additional term thanks to that decomposition I showed at the top of the slide. And that additional term says, if you want to upper bound it by the largest error, estimation error difference. So the largest of all of the interpolation points or perturbed points, this difference, right? So I'd like that would be added to this model error analysis. Okay, so now you can see that this first term, as before, is only dependent on delta k. I have the error estimate in the differences, Clearly, if I want everything here to be ordered delta k squared, again, I would need the error estimates to also be ordered delta k squared. And I would need it for all of my interpolation points and also at the point that I'm interested in. This will ultimately be the candidate point that we want to evaluate and decide to accept or reject. Here, as you remember, we will be able to say that we have this result with a probability since we are dealing with random things. Okay. So in addition to the previous roles that delta was playing, now in the stochastic setting, it's also going to play the role of controlling the error estimation. And I did want to say that, in fact, even for the first order oracles, so both zeroth order and first order oracles, DFO convergence analysis is relevant because in both cases, even when we do have first order information, we still are dealing with inexact, noisy gradient estimates. So the steps that I was showing before would still need to be handled similarly, even in the first order setting. Both model quality and criticality have to be taken into account when we're analyzing model-based algorithms for stochastic oracles. Okay, so the algorithm is going to be identical to what you have seen before. The main changes are that your model is going to be probabilistically fully linear, if you recall that concept, which means that your model error is going to be ordered delta k squared and your model gradient is going to be ordered delta k. And then you will do the same thing of, okay, build the model and have ensure that it is probabilistically fully linear, then minimize it within your delta k. That's going to give you a step size sk, and I'm going to use this notation x of k superscript s, which is basically the candidate solution, and then we'll evaluate the achieved or estimated improvement compared to the predicted improvement from the model. Notice that at these different points, I might have different sample sizes, so I use an nk superscript s. And then for acceptance and rejection, I use the exact rule that you saw in the earlier lectures, where we check this ratio, rho k, as well as the criticality condition, which has to do with the gradient, model gradient, and delta, making sure that if our model gradient is too small, even if we get a sufficient reduction, we still won't accept a solution because of inexactness of our gradient estimates. And convergence theory, as before, very similar to the deterministic setting. We're going to have the previous assumptions that you have seen of Lipschitz grads and bounded below functions. We're going to have a Cauchy decrease requirement or a fraction of Cauchy decrease requirement when we are computing our subproblem or SK step, and then uniformly bounded model Hessian. So this is all what you've seen before. But we do need to think about this. How do we get this fully linear probabilistically fully linear model, right? The way that we can do this is by ensuring, as we saw in the earlier slide, is that these difference errors are going to be order delta k squared. Sorry, there's a square missing in this slide. But I would need to ensure that with some probability. So let's talk about that a little bit. The central limit theorem in statistics implies that if you had a fixed xk and you ran your simulation with IID samples, letting our gradient, calling our variance of the function sigma k, then central limit theorem says that the error, since I have unbiased function values, is going to be bounded in probability by this at this rate, sigma k divided by square root of n. To put it in simpler terms, what that means is that if I was interested in how large my error is, if I scaled it with that sigma k divided by square root n, and I wanted to know what's the probability of this scaled error being less than some arbitrary kappa, then I can use a standard normal to get this probability, right? So as my sample size increases, I can do this. Okay, so but what does that mean for us here? This is the error bound that we needed. We needed our errors to be bounded by some kappa r delta k square, and we want it to be with a fixed probability. So I would like to pick this n to be such that this phi value is going to be greater than beta, right? So if I fixed my probability, then I can pick my n accordingly. And you can see at the bottom that I work out the math there. So you can see that my n is going to be proportional to that variance multiplied by 1 over the fourth power of delta k. So if delta k is going to get small, this means my sample size is going to increase at that very rapid rate. We can do this either for each point that we are evaluating or for the differences, because recall in our analysis, we really need the difference to be less than this kappa r times delta k squared. So since we can use the differences, this gives us that opportunity to use the variance reduction. Again, with variances, we know for two random variables, the v and w, you have a this is equal to variance of v plus variance of w minus 2 times the covariance of v and w, right? So if I was able to induce a positive correlation between v and w, then I can reduce this variance of difference. And that's really the idea here. So I want to ensure that this difference is of the delta k squared order with a probability at least beta. And so now I'm going to define the square root of the variance of the difference as sigma k superscript d. And so if I do the analysis that I did before, you will see that I will have this n is going to be the variance of the difference times delta k to the minus 4. But now I can actually show that this variance of the difference is itself going to decrease or be proportional to the step size. And I'm not going to talk about the proofs of this, but it actually comes from, again, structure of our random functions. In fact, in our we can prove that if you used independent samples at two different points. So what two different points am I talking about? I'm talking about xk and xki. If I used independent samples for these, I would get what I had earlier. But if I did use common random numbers, so I used the same random number stream, without additional structure, my variance is itself going to be proportional to delta k. What this means is if you plug that into the red formula above, you will see that the power of your delta k basically is going to be smaller in a way, which means that your sampling rate is going to be smaller. So this is one way that we can actually use less samples but get the same variance in the difference as we would like. And we can do this even more if we have more structure in our random functions. In particular, if our random functions are themselves Lipschitz continuous, then you can actually show that you only need delta k to the minus 2 as your sampling rate for the sample size. Okay, so how do we deal with this error control? Everything that we talked about so far is good, except that I really don't know what this sigma square that we've been looking at is. In the previous slide, I said if we assume that we have everything bounded by a sigma max, then I can get that result. But in practice, I don't know what this value is, right? So I can do something similar to what we do when we don't know the Lipschitz constant, and we have a procedure for adaptively choosing our step size to be basically learn the local Lipschitz constant, for example. So the same kind of idea can be used for choosing the sample size adaptively, in that we want to find the local variability as opposed to a maximum variability. And therefore, we will only use more samples when there is larger variability and smaller samples where there is less variability. And that's what the idea of adaptive sampling is. And if you think of, okay, if I wanted to do this in a naive way, I could start with a N0 pilot samples to get an estimate of local variability. So I have a sigma hat. I plug that sigma hat into the formula in the previous slide, and that will give me a sample size. The issue with this is that sigma hat you get could be a very bad estimate of sigma if you started with a small sample size. So a better idea is to actually do this sequentially. So you keep adding samples until the error falls below the threshold that you're interested in. Okay? And the problem with this is that you will, in a way, lose that independence or IID that we were discussing, because if you have a sequential selection, at the stopping time, when you stop adding more samples, is when you basically have used the information from the previous samples to know how large or how small your error has been. But thanks to a sequential estimation theory by Ghosh and Mukhopadhyay in 1984, we know that we can still analyze random variables whose sample sizes are stopping times and are sequentially selected. Okay, so if I have a random variable y with some of its moments bounded, in particular at least the first 8 moments bounded, then if I choose a sample size as such, okay, so let's look at this sample size. It says keep adding samples, maybe start from a lambda value and keep adding samples until a standard error of your estimate falls below this right-hand side, kappa over square root of lambda. And they show that as this lambda goes to infinity, you can actually have the second moment of your estimate is going to be proportional to the square of the right-hand side here. Okay, so standard error is what that estimation error is going to be. That quantifies the estimation error in a way. So if I just kind of flash back to what we did earlier in today's lecture with sample average approximation, right? Sample average approximation, as you saw in Shapiro's results, in order to make sure that you get good estimates, you need that very good estimate everywhere. So you would need to pick a very large sample size for all of the points you're evaluating. If I was trying to get to the optimal solution here, I would need a small standard error for all of the points. Whereas in an adaptive sampling rule now, if I did something for that right-hand side that told me I only need the error to be as small as what I need it to be, which for us ends up being delta k squared, then when you are far from optimality, for example, you're sitting at this x4, your delta k is larger, which means that your right-hand side is large. So you're not going to need as many samples to bring this standard error down. And so even with a large standard error, you see that with the confidence intervals, you're still able to find a better solution and move along towards your optimality. And as you're getting closer and closer up, you want these errors to get smaller so you can correctly identify where you find better solutions.
About the 2-minute warning, Sarah.
Oh, okay. So let me just talk about the guarantee of this adaptive sampling. I'm just going to show you a Borel-Cantelli lemma that says, okay, this was the error that I wanted. I actually wanted 1 minus this, but we can start with this error being large. I can do a Chebyshev and plug in my second moment following the result I showed you in the previous slide, and then it will give me a value like this. This gives me an opportunity to say, okay, so this probability is going to be small if I choose my lambda to go to infinity, right? With k, with iteration number k. If I did that fast enough, if I chose this to go fast enough, in a sense that I would make this probability summable. In probability theory, we can apply Borel-Cantelli's lemma to say that the bad events will infinitely often happen with probability 0, which means that If I run my algorithm long enough, for k large enough, I will have the good event happening with probability 1. And this is where we get to that with probability 1 result that I was talking about. So we were able to prove this result for our AstroDF algorithm, as I said. And what this means is your sample size is growing at this rate, and this is not ideal because this k is the first iteration, if you think of it. This k is going to be, or you can expect it to be as large as epsilon to the -2, which gives me a very large sample size, epsilon to the -6, at least a lower bound for that. So how do I do better than that? I'm going to go quickly on this slide to say that in addition, if I had in addition to finite variances, I knew something about the tail distribution or tail of my random noise, then, for example, if I knew that it has an sub-exponential tail, which is a heavier tail than a Gaussian tail, I'll be able to actually change the analysis by applying, instead of a Chebyshev, a tail probability bound. And what that means is, in order to make that summable probability and apply Borel-Cantelli lemma, now I only need logarithmic k for my lambda k. So this reduces my sample size to epsilon to the -4 times the log of epsilon to the -1. And this slide is really to say that the analysis is pretty much similar to what you have seen before. In the deterministic setting, we start by saying that once your delta becomes small, you become very successful. Then before you reach epsilon stationarity, you can lower bound your delta k. You recall this result. And from there, we can show how much progress we make in every successful iteration and finally prove convergence. It turns out you can do similar steps, but you will start with that accurate estimates to prove that you will eventually have them with probability 1. And therefore, you can basically carry through this with probability 1 guarantee for all of these results and reach your with probability 1 convergence. Okay, since I have run out of time, I will leave this. If there were questions, I can come back to this. In order to get total complexity results, which is what you see in this table, we will also need to know how many points we need to evaluate in the derivative-free setting. And so in this table, I have the two rules that you saw in earlier lectures, where I would use perturbation size to be delta k versus delta k divided by square root of d, and how that pans out in terms of the total sample complexity of AstroDF. So with that, I would like to just have final remarks of the choice of adaptive sample sizes can be helpful in practice, but also for proving almost sure convergence and proving almost sure complexity results. You can use variance reduction. You can do additional things, which I didn't have time to go over today, but I'll be happy to talk about those. Further improvement of the complexity results, as well as other sampling strategies, for example, stratified sampling, and also in more complicated settings like in constrained stochastic optimization. So sorry we went a few minutes over, and thank you for your attention.
Okay, thank you very much, Sarah. It's a very nice way to round out the week. I know we're late, so if people have to run off, please do, but happy to answer questions as well, hopefully. So if you've got any questions, please yell out. If not, I might just ask questions out of my curiosity, which is the examples like the news vendor and the bus arrival problems, the sample paths aren't smooth. They've got discontinuities, they've got gradient discontinuities. How does that affect your CRN theory, at least?
So CRN, you have the case, if I go to the CRN results, if you do have smoothness in your sample paths, you can use the lowest rate of sampling. Let me see if I can find that. I think it's right here. So that would be this bottom case, where my sample size is going to be delta to the -2. But even if I didn't have Lipschitz continuity, as long as I use common random numbers, I can still reduce the rate of sample from epsilon delta to the delta k to the -4 down to delta k to the -3.
Okay. And
In
that's even if the
practice,
sample paths are discontinuous, or do you still require like Lipschitz continuity or something of the function?
so here we don't use anything about the sample paths
Okay.
structure. Yeah. So I believe that even discontinuity wouldn't invalidate this. What we use here, which I didn't go over, is some sort of structure in the variance function. So as long as your variances don't hugely
Right.
change, if then you should be able to get better sampling rate even without continuity of sample paths.
Okay. And I guess relatedly then, if we keep upping the assumptions, if the sample paths are like C infinity or anything, does that give you even more structure, or is sort of the bottom line that you've got there about as good as you can hope for realistically?
No, I think that we can definitely, if there's more structure, we should be able to get better results. The the reason we didn't do more than this is because in black box settings, really, even this much structure might be harder to justify.
Yeah.
But yeah, I believe that you can get better or smaller sampling rates when you have more structure.
Okay. Great. Okay. If there's any other questions, we can ask them. But if not, I'll say thanks to Sarah again, and I'll stop the recording now.
All
So
right,
thank
thank you.
you, Sarah.